to start introducing chapter 6. And for chapter 6, we're going to find that it has to do with work and energy, okay? I updated this and it seems that, okay, let me see. All right, I will start talking today about work and energy, and we're going to just talk about kinetic today. And chapter 7, we are going to talk about gravitational potential energy and more general conservation of energy. Okay. Okay, then for this week, okay, done, close. We are going to understand what does it mean to do work on an object. Then we are going to start talking about the idea of calculating the work. And one thing that I want to say here is that most of the time we are going to find some of the terms in physics. They doesn't mean the exact meaning in the daily life language. We will also introduce the kinetic energy, which is the energy of motion of an object. And we are going to relate the work done, the total work done to the kinetic energy of the system. Also, we are going to use the relationship between total work or the net work and change in kinetic energy when the forces are not constant and when the object is following a curved path. Finally, we will be able to introduce the concept of power and related to the rate of doing work. Now, this baseball here, this baseball ball, there was a pitcher who does work on it so that it will give it what is called kinetic energy. And we are going to introduce now what does it mean that there is a work, and what does it mean also to have the kinetic energy, and how this is really connected to the concepts that we already introduced before. Now, there is most of the time a force acting on the object, and if that force was successful in moving the object at displacement S, then there is work done on that object. Now, I will say maybe here in this exact example we have W equals Fs, but I'm going to say that the work, it is the force times displacement, this is the most general, times cosine the angle between the two vectors. Then every time you are going to introduce the work or you want to calculate the work, you should worry about the magnitude of the force, the magnitude of the displacement, and cosine the angle between them. Work, it is a scalar quantity because it is resulting from the dot product of F dot S. Okay, remember we introduced in chapter 1 two types of multiplication. One we did call it like scalar or dot multiplication, and the other one we call it vector product or vector multiplication. Okay, and that one or cross product, and that is another thing. Based on this, we're gonna find that I can define the unit for work as in newtons times meters, which is kilograms times meters squared divided by seconds squared, which is really very convenient to call it joule as an appreciation for Mr. Joule, and also it's gonna be very easy for us to use. That work depends on the force F, the displacement S, and of course cosine the angle between the two, or the angle between them. In the common examples, these are really just short of, let's say, thought experiments that I'm gonna move you through, like how the angle is going to affect the magnitude of work. In the first one, I have an example about a force that is 20 newtons pulling the object to the right, and in the same time, it is causing a displacement that is really, in the same direction, which is 2 meters. Now, I want you to notice here that this is the direction of the force and this is the direction of the displacement. It's always very helpful maybe to say this is F and maybe this is S, just to show what is really the angle between the two vectors. And here you can see that they are both pointing to the right, which is making them having an angle 0 between them. And when you click on your calculator and find cosine 0 is going to be 1. Then this is the maximum work that I can get from a force. When the force and the displacement are in the same direction, then the work done is going to be the 20 newtons times 2 times 1, which is going to be 40 joules. All right? Now let's assume for the same displacement and for the same force, I did increase the angle to be 60. Okay, you can see here that the force, here, the force and the displacement, they have 60 degrees between them. Now, just a reminder that this angle is not measured from the positive x-axis. It is actually measured between the two vectors. Then W here, the work done, is going to be the 20, which is the force, times S times cosine the angle, and the angle now is 60, and cosine 60 is 0.5. Then I will get the work done as 20 joules. The third example here is, let's assume I have, I can actually say it's gonna be 20, again, 20 newtons upward, and the object is moving to the right with displacement 2 meters. Then I will say the work done is gonna be the force times S times cosine 90, and you can find that cosine 90 is 0. Now, there is a difference between carrying an object and lifting. These are two different, I will say, processes. In this example here, I'm showing you I am carrying a box, let's say, that is a 20 in newtons weight. Okay, then in order to carry it, I need to overcome the 20 newton, and I am moving to the right. Then now my force of, I will say, carrying it should be upward, and I will say the displacement is to the right, then this is 90 degrees. Now when I lift, is going to be different. I will have the force upward, and at the same time, I have the displacement in the same direction, okay? And this is really showing here that when it is lifting, it is different than if I have, again, the same weight, which is 20 in newtons times 2 meters. I'm going to lift it 2 meters. Then again, I will apply like 40 joules of work. In number 4 here, I assume here I have a force that it is in the opposite direction of the motion, then this is motion direction. And I assume this is a force of friction that is acting to the left, and it is 5 newtons. And if you can see here, this is the direction for S, and the direction of the force is in the opposite direction. And here I have cosine 180, and that cosine 180 is going to be negative, and then 5 times 2 is going to be 10, then it is going to be negative 10 joules. And that is really when I have any force that is opposing the motion, like air resistance, friction between solid and solid, any force that is going to try to hinder the motion or slow the object down. The SI unit of work, of course, it is joule, and it is named in the honor of the 19th century English physicist James Joule. And I will say the unit of joule equals, of course, 1 Newton times meter, or, as I said, since the Newton, it is kilograms meters per second square, then in Newton times meters is going to be kilograms meters squared divided by second square. And here in this calculation that I was talking to you, we're assuming that the force is going to stay constant and it will not change its magnitude. And we are going to see now how we are going to deal, like later, how we are going to deal with situations when the force it's not I would say a constant. It's going to be like changing. And here, this is the definition of work as F dot S. What I have here, again, it is a summary of what I went over, which is talking about how really the angle is going to affect the magnitude of the work. Then if the force is making an angle less than 90, the work is positive. If I will say there is a component of the force in the direction that is opposite to the motion, the work is going to be negative, which means if the angle is more than 90, the work is going to be negative. And of course, if it is 90, we are going to get that the work done is 0. Here, a weightlifter does no work on a barbell as long as he holds it stationary. If he or she is lifting, then that is going to be different. Lowering here, then there is work and that, of course, positive work because the force and the force and the displacement are in the same direction. There are many occasions where I don't have a single force acting on the object, and therefore we are going to talk about work total. Now, the idea of work total is going to be, like I will say, we have two options to do that. Either, okay, this is one approach, is to calculate first the net force, and then I will say the work total is going to be the net force times SO, okay, or let's say sigma F times the S cosine the angle. This is like it can be done. Or, okay, the second approach is I will calculate the work done by each force, and then add all work magnitudes together. Then work total can be work of force 1 plus work of force 2 plus work of force 3, bum, 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 bum. All right, now I want to show you one example where I will do this. And here, this is my example is where I have an object here. You pull a box over a rough surface using a force F that has a magnitude of 20 newtons, making an angle of 60 degrees with the positive x-axis. The surface has a kinetic coefficient, has a coefficient of kinetic, has a coefficient of kinetic friction, mu k equals 0.15, and the object moves 2 meters to the right, and the question is to calculate the net work on the box. Okay, now always a sketch is helpful. Then I know that this surface is rough. It has a mu k of 0.150, s is 2 meters, and the force is 20 newtons, and making an angle of 60, and the mass also was given as 2 kilograms. Okay, because I need it for the calculation of friction. I will say the steps here for the calculation. You are going first to sketch. Just make like a diagram. You need to draw free body diagram because you need to identify all the forces. Now also, I might use a Newton's laws to determine one of the unknown forces like friction. Then like in this question here, mu k was given, but I don't have what is really the total, or like what's the value of the friction. And then I will calculate all the work. This is my approach that I like to do, which is calculate the work done by all the forces. And then I'm gonna add the work from all the forces, and I'm gonna call this W total, and I will add all the works done by each force. This is my diagram, okay, for all the forces acting on the object. There is, of course, that force, the 20 newtons. There is a normal, there is an mg, and there is an fk. This one, remember, like in your last exam, I have so many, they're going to say this is muk. Muk is not a force. Fk is the force. Now, also, as I said, we need maybe to use a new, this is really the first, like this was the sketch. This is step 2, which is free body diagrams. This is step 3, where I'm gonna apply a Newton's laws to calculate what is really the, unknown force. And here I need to determine first what is really the normal force in order for me to calculate what is really the force of friction. Because remember, Fk, it is mu k times normal, then I need first to find the normal and then to calculate Fk. Here, of course, I did apply. I don't need the x component here. I need only the y component. Then I will say sigma Fy equals 0. And from the diagram, I can say that n plus f sine 60 minus mg should equal 0. Then the normal equals mg minus f sine 60. And I have calculated this as 2.28 in newtons. And then after that, this is the step where I have calculated what is Fk. Then now for the word net, I will say it is the work done by the force, the work done by the normal, the work done by mg, and the work done by friction. Now here for the first force, the forward force, Fs cosine 60, and for the friction, it is, of course, Fk times S cosine 180, because the force of friction, it's opposite to the motion. Now, for the work done by the normal, it is the normal times S times cosine 90, and therefore it's going to be 0. And for the work done by mg, or by the weight, again, mg times S cosine 90, and therefore is going to be 0 as well. Then here I have calculated what is really the work done by the forward force, what is the work done by friction, and then I have my total as 19.3. Now I can start by talking about kinetic energy, and maybe also, a very important theory here that we usually use, which is called work energy theorem. This really, I will say, this theorem is very important in determining what is really the initial velocity of the cars when we have a car accident. Now, you know this equation from before, the V final squared equals V initial squared plus 2A delta X, and then V final squared equals VI squared plus 2AS. And that is, I will now also multiply all the terms with 1/2 m, then here, multiply by 1/2 m, and that is going to be 1/2 mv final squared equals 1/2 mvi squared. Here the two will cancel, then I'm going to have m times a times s, and that is sigma f equals ma. I define now something called kinetic energy, then it is 1/2 mv squared. Then I can say this is K final, this is K initial, and that is sigma F multiplied by S. And remember, this is the work total. I can bring the Ki to the other side. Then work total is K final minus K initial, or it is delta K. Remember that delta K can be positive, can be negative, can be 0. okay? And it is always final minus initial. Don't put it like always positive. It depends on what is your initial, what is your final. This term here, which we call it, kinetic energy, it is the energy of motion. It is a scalar. It equals 1/2 mass times v squared. And mass should be here in kilograms. V, we can say here's the speed since it's a scalar v dot v. And of course, again, it has units of joules or kilograms, meters squared per second squared. Okay, I'm gonna stop here so that my video will not be very long, and I'll continue in another video for chapter 6. Thank you.